Okay, so we've got this intermembrane space, and so we're going to blow this up, but in terms of the electron transport chain, we have three little complexes here that are in the membrane electron transport chain, and you're going to have your cofactors come in, and what these guys are going to do is they're going to pump protons out of the matrix into the intermembrane space. And then what we won't focus on today, but we'll focus on next lecture, is those protons can then come back in, and when they do that, they're going to come in through the ATPase synthase, and we're going to go to ADP to ATP. Okay, drawn tiny and almost pretty illegible. Okay, but overall, that's what's happening here. We're going to blow up and look in greater detail at what's going on that intermembrane. But that's essentially our process, and that's how ATP is going to get made here. Questions? All right, let's blow things up and look at it bigger and in more detail. So what we've got is we've got this mitochondrial membrane here. And we're going to have, actually, let me give myself a little more room. We're going to have a membrane, and we're going to have three complexes here in it. Complex 1, Complex 3, Complex 2. But Dr. Johan, what happened? Sorry, Complex 1, Complex 3, Complex 4. And you might say, Dr. Johan, what happened to complex 2? Well, it's the succinate dehydrogenase that's in the citric acid cycle. So that's actually in the membrane. That's the one that makes the QH2. But that's how that numbering ended up. And then what we have is here I'm actually, so this is the intermembrane space. And this is the matrix. And for this figure, previously I hadn't been super careful. I am going to make sure I get things on the right side of the membrane, okay, in terms of what they're happening. I don't care if you get it right, but I'm going to get it right here. Okay. So we have NAD+. This is going to happen inside in the matrix, which makes sense. You have, I'm sorry, wrong way. NADH is going to go to NAD+, right? The NADH is going to come in and it's going to drop off its electrons into complex 1. Those electrons are going to go through, complex 1. Okay, as they go through complex 1, they're going to drop from higher to lower energy, and that energy for those 2 electrons, remember this is a 2-electron transfer, is going to cause 4 protons to be pumped across the membrane. On the other side of complex 1, I'm drawing this as a left to right thing. It's not really that, okay? But we can think about it that way. On the other side, we're going to have, in the membrane, we have ubiquinone is going to come and it's going to pick up those 2 electrons and become ubiquinol. Okay? It's going to move across till it gets to complex 3, and it's going to drop off those electrons and become ubiquinone again. All right, so we're transferring 2 electrons from complex 1 to complex 3 using ubiquinol. Those electrons are going to get into complex 3. They're going to go through complex 3, and as they do, they're going to drop from higher to lower energy, right? So here we start way up here in energy. We get lower, maybe coming out to here, coming out of complex 1, and then we're going to go lower. right? We're going lower in energy for those electrons as we go across, and some of that energy is being captured to pump protons across the membrane. So here we get another 4 protons, and the energy that doesn't get captured, what happens to it? Gets lost as heat, right? Okay.
Why is it one proton for every 2 electrons?
2 electrons. It's just the mechanism inside the complexes. I don't know it well, and it may be described a little better in your textbook, and certainly a more detailed. I have picked a textbook that is fairly run down the middle and not a lot of extra details. If you had a textbook that had a lot more details, they may give you a lot about what the mechanism is, but we're not going to worry about it in here. And then what we have is we're going to have a protein called cytochrome C that has an iron in it that's going to pick up the electrons here. So we will have cytochrome C, okay, with iron 3 plus. I'm going to run out of room here. And it's going to pick up an electron, and it's going to make cytochrome C with iron 2 plus. Right, and we're going to have that same cycle. I drew my cycle inside complex. Maybe I'll move complex 4. That's probably the best solution here. We'll back complex 4 off so we have a little more room. Okay, so we have complex 4 there. And what do you see anything wrong here with what's going on with our cytochrome C?
Fe3 is bad.
Well, Fe3 is bad, right? But it's okay as long as it's in an enzyme away from where it can do bad things. It's really Fe2 going to Fe3 is bad because what that does is it's going to produce hydroxyl radicals. It's a reduction. It's going to cause us to get some radicals, but it's not a problem here. Fe3 to Fe2 is only 1 electron, right?
Mm-hmm.
But this is a 2 electron process. So this has to happen times 2. Pick up 1, move it over, pick up 1, move it over. There's more than 1 of these, so that could be happening simultaneously. Those electrons get to complex 4, and we get 2 protons pumped as they move across the complex. Okay, those 2 electrons. So it's 2 protons for the 2 electrons. It's not half as many because of what's going on with the cytochromes. And then finally, over here on the inside, in the inside of the membrane, we have our oxygen is going to pick up those electrons, and their final resting state is going to be a very stable water molecule. Okay, and we know water is not super reactive, right? It's not giving up electrons to things very easily. Questions? And I'm not going to bother drawing it. I've drawn it before. I'm not going to draw it now. Those protons then will come over, and at least most of them are going to come over and go through the ATP synthase.
Wait, so sorry, you said only 2 of the last one?
It's only 2 protons pumped, okay. So 10 protons total. But this is actually, when we think about the protons pumped here, this is something that can explain to us why we have the PO ratios we have for NADH and ubiquinol. All right. So if we think about this, we think about NADH PO ratio is going to be 2.5, right? We get 2.5 ATP out of it. And if we think about ubiquinol PO ratio, that's going to be 1.5. All right, let's think about those ratios. So we have 2.5 on top. Let's just do it as a ratio thing like this. And then on top, on the other side, we have how many protons are pumped by when we run an NADH through? 10. What if, so I'm just going to put NADH NADH, just to remind us here. And then what if we took ubiquinol, where would we start? Ubiquinol comes in. And this is just in the membrane, not on one side or the other. But it's 6, right? So for 1.5 for ubiquinol and 6. You see how those ratios match up? If I take 2.5 times 4, I get 10, right? Mm-hmm. If I take 1.5 times 4, I get 6. They're the same ratio. Mm-hmm. So it's based on how many protons are pumped is how much ATP you get, which makes sense because the protons are coming through an ATPase. Does that make sense? All right, so let's think then up here about, let's do an overall reaction for this, okay? So our overall reaction here is, we'll do another one of these things where we think about it. Let's just pile them all together down here. All right, so what do I have at the beginning of this thing? At the beginning of the electron transport chain, I have NADH, right? It's going to go to NAD plus. Okay, I'm gonna not worry about extra little hydrogens and stuff for what we're doing here at this point. So then the electrons go through, and what do we get? We get ubiquinol, picks them up, and becomes ubiquinone, right? I said the names wrong. Yes, I drew it correctly, but you're right. Yeah. Ubiquinone picks up so we have this as a reaction, right? And then ubiquinol drops off its electrons and becomes ubiquinone. So I have this. My cat does this on my computer all the time. I did it right there. I don't know how. I'll have to ask my cat. All right, so ubiquinol goes to ubiquinone to drop off those electrons at the next complex, at complex 3. All right, we'll go up there. Then we have cytochrome C, right? We're going to have 2 cytochrome Cs, iron plus 3, are going to pick up electrons to make 2 cytochrome Cs, iron plus 2. I should do 2 plus. Formally, it's that way. It's the best way to write it. And then those cytochrome Cs wander off to complex 4 and drop off their electrons. So we have 2 cytochrome Cs at iron plus 2 become 2 cytochrome Cs at iron plus 3. And then finally, what we have is those electrons wander across complex 4, and we have 1/2 oxygen, diatomic oxygen, so 1 oxygen atom, picks up those electrons with some hydrogens and becomes water. Okay? And so we have this thing, this isn't a cycle, but we have this thing where a lot of those intermediates in the middle, they become something and then they get reverted back to what they were. My ubiquinone can cancel, my ubiquinols cancel, my cytochrome Cs plus 3 cancel, my plus 2s cancel. And so my overall reaction here is, I'm going to go NADH plus 1/2 oxygen goes to make NAD plus water, right? That's my overall reaction, plus 4 protons pumped. No, 10 protons pumped, sorry. Okay, that's pumped at the end there. Okay, that's our overall reaction. Questions? Okay, then this is the point where electrochemistry rears its possibly confusing head. Okay, this is where what we can do is we can calculate the energies of these reactions, right? All the individual reactions, we can also calculate the energies of specific ones. All right, I want to remind you that our electrochemistry is equal to, or can be converted into our free energies that we're used to. So if we think about the standard biochemical free energy of a given reaction, that's equal to N, which is the number of electrons transferred in whatever reactions we're talking about, times Faraday's constant, times the potential of those reactions. Okay? And I want to, so this is number of electrons. Don't put the sign with them. We've got a negative sign out already. And this is Faraday's constant. And that's 96,500 joules per volt mole. Okay. Questions?
Why?
Why is that the case?
No, why do we care?
Oh, why do we care? That's a great question. So we can think about whether these reactions are spontaneous. Okay. In terms of the driving force of thinking about electron transport chains, and in terms of evaluating other electron transport chains. This is not the only electron transport chain. Mm-hmm. If you think about what happens in, I may talk about this in a lecture or two, but you think about what happens in like a septic system. So septic system, you're breaking down essentially nitrogen containing compounds, and you get different reactions depending on whether there's oxygen around or not. And so eventually what has to happen in these systems to really to take all that nitrogen and to turn it back into, I think you're turning it into gaseous nitrogen in the end. I haven't looked at it in a couple of years. But you have a set of electron transport chain type reactions where your final electron acceptors don't have oxygen in them because there's no oxygen around. So they're examples of these sorts of things where you have different final electron acceptors that are not oxygen because it's not present. So why don't we go ahead and let's go ahead and calculate. Let's use this table here to calculate the potential change here. Okay, talk about the potential change here of these, and then we'll convert it to a delta G for this overall reaction. All right, so we start out with NADH, right? And plus we're going to go 1/2 oxygen. And once again, I don't want to obsess over all the protons. There's another proton in here. I'll go ahead and draw it, but I don't care so much that you get that. And that's going to go ahead to make NADH, no, not NADH, NAD plus H2O. Okay. We can break this up into 2 half reactions, and that's what we got for our table over here. We've got half reactions. What happens when we're doing electrochemistry? Hopefully you remember this from Gen Chem, but what happens when I flip this one, you know, just because we always select this. When I flip one of these, what happens to my potential? I flip the sign over here, okay? But let's go ahead, and so good. And for potentials, positive is spontaneous, okay? Which is why we need this, we look at our equation up here, why we need this little negative sign here. Because if positive is spontaneous, we need to change it negative for it to be spontaneous over on the free energy side. There's another rule with these. This is actually last time I took a practice MCAT, I missed this question. I got a perfect score in the physics section. I missed one in the chemistry section, which is embarrassing. But this is what I missed. Okay, so what you've got is if you take one of these and you multiply them times a number, like what we're doing with our cytochrome C reaction, right? We have two of those that happen. What happens to the potential if we have two of them? It does not change. It does not change. Okay? So the way to think about this is when we think about a water tower. You've got a water tower, and the height of the water tower is the potential energy of that water tower. The height of the water tower plus how much water's in it and can flow through is how much energy you get out. So when we talk about the energy, that's the height of that water tower plus how many electrons are going through. Not the height. It doesn't matter how many electrons there are. It doesn't change the height. Does that make sense? It doesn't matter how much water's up there. It doesn't change how high it is. That's how potential relates to, that's a way of thinking how potential relates to free energy. Okay, so if we look here, then we're not going to have to worry about that rule here, but we are going to have to worry about it possibly someplace else, because all these things are like two, there's no doubles here, okay? But if we look for our reactions, then here we have this one, right? Is it written in the same direction? Yeah, it is, right? Oxygen going to water. All right, so if we think about this reaction being the sum of the half reactions we see over on the left, we have 1/2 oxygen. We'll go ahead and put the electrons in. We'll go ahead and pull in our hydrogens here, but we're not going to worry. We're not going to obsess over those. 2- goes to water, right? And that's going to give me a potential of 0.815 volts, the whopping 0.815 volts. You guys may not feel that way about it, but I feel like it's whopping. And then our other reaction here, this is a reduction potential. So it's it being reduced, but is our NADH being reduced? No, it's the reverse reaction. So we need to flip it, and then we also need to flip the sign of our potential. And so that's going to be 2 electrons. Actually, let me make it more obvious where that arrow is. And then we're going to go NAD plus H plus 2 electrons. And we flipped our sign, so now it's 0.315 volts. Do you see that I can cancel these electrons? I can cancel this proton with one of these protons. And if I add these two reactions together right here, I get that reaction. And what's left down here. Okay. And so then I'm going to add up those two potentials. Oh my God, I should be able to do that in my head. 0. Oh, don't help. Is it a 3? 1.130 volts. There we go.
I did it.
Yeah, good.
I only did it because I had to.
So that's a more whopping 1.1 volts. All right, so let's go ahead and see how much we're maybe more familiar with how big things are for free energy. So remember our free energy equation here is equal to negative n Faraday's constant times that potential. And so we have how many electrons being transferred here? We canceled them out, but they were there. 2. Negative 2 times Faraday's constant, which is 96,500 joules per volt mole. And that's times our potential, which is 1.130 volts. Okay? And so it's going to be a lot of joules, right? 2 times 96,500. Oh, I'll turn my calculator off. 2 times 96,500 times 1.13 equals 218,000 essentially joules. I rounded 218,000 or 218 kilojoules.
Is it negative?
Yes, and it's negative. Thank you. Spontaneous.
Kilojoules or kilojoules per mole?
Per mole, you're right.
Wait, it's not spontaneous.
Does that seem like a big number for you?
Yes.
What's this number for the formation making an ATP? We take ADP plus phosphate and we go ahead and make ATP from it. Have you accidentally memorized that number?
I did, and then I forgot it.
You forgot it. It is net. I love breaks. It's kilojoules per mole, right? So how many ATP, if we captured all that energy, how many ATP could we make?
More than 2.
How many? More than 2.5. How many ATP could be made from if all the energy was captured from the 2 electrons, well, from the overall reaction for the electron transport chain. Okay, so what we're talking about here is how much energy could we capture? This is taking those 2 electrons from NADH and getting them all the way over into water. Yes?
Wouldn't it be positive 30 because that would be the non-spontaneous going from ATP?
Sure. Agreed. Okay, but what we're going to do here is we're just going to take 218, right? That's going to be 218 kilojoules produced or captured. Okay, and if I captured 30.5 kilojoules captured, I just made up a conversion factor, I would make 1 ATP, right? 1 ATP made. And it's easy to cancel units if you've made them up. 218.
It's like 7.14.
Yeah, 7.184. How efficient is this process? No.
No?
How many ATP do we actually get from it?
30. No.
2.5.
Oh.
Right? So we get 2.5 ATP in reality. So if I take 2.5 and divide it by 7.14 and multiply by 100, I get 35%. Okay, so let's go ahead and 2.5 ATP made, 7.14 ATP theoretical. Right, this is our yield. Times 100, that's 35%. So we lose a lot of this energy to heat. Questions? Okay, I can stop there. Are there any questions about stuff we're doing? Yes.
So it talks about like positives are spontaneous for the concentrics. So we had like positive 1.1.
Yes. Yes.
That's spontaneous.
That's spontaneous.
It's a formula. It was with negative sign in the formula.
Yes.
So then now negative is spontaneous.
So it takes care of the difference in sign between potentials and between reduction potential between the free energy. And the reason why those signs are different is just some historical thing. Whoever came up with electrochemistry thought positives would be fun.
That was some like only a little addition. It's you don't have to have a couple of biochemistry layers in one. That's most really.
Oh, I didn't hand back quizzes. Do you guys want quizzes? Yeah. Did I somehow hand back quizzes? Feels like I don't have enough. I did because most of you actually came to class. Bless you.
If we could hear him, we would have to get. I watched it this week. It did cut in and out a little bit, but. No, when he asked me about that. Yeah, because,